In this video, we take a look at Markov chains. So this is our introduction to Markov chains. And our objective in this video is to learn how to write and use a Markov matrix, also known as a stochastic matrix. So the term stochastic means regarding conjecture. So we say that an n by n matrix is a stochastic matrix when each entry is a number between 0 and 1, because we're thinking about these as probability matrices. So let's consider a situation in which members of a population occupy a finite number of states, and we'll call those states S1 through Sn with the subscript to denote which state we're in. For example, a multinational company has $4 trillion in assets. So we're going to treat those $4 trillion as the population that the company has to move around. Some of the money is in the Americas, some is in Asia, and the rest is in Europe. So those are our 3 states. In a Markov process, at each discrete step, so discrete means it's not continuous, it just happens one step at a time. Members of the population, in this case, the $4 trillion in assets, may move from one state to another, subject to these following rules. The rule 1, the total number of individuals stays the same. So in terms of our population here, that means the company maintains the $4 trillion in assets. They don't take anything in or out. Number 2, the number in each state never becomes negative. So you can't have less than 0 in each state. And number 3, the new state depends only on the current state. So we don't look at the past history. All of our calculations start from the current state, and then we move from there. The behavior of a Markov process is described by a matrix of transition probabilities. So if you look at my matrix over here at right, you notice all of the entries are denoted P because they are probabilities. They're values between 0 and 1. This is also known as a stochastic matrix or a Markov matrix. So Pij is a probability that a member of the population will change from the jth state to the I state. So J corresponds with the row, or sorry, with the column, and I corresponds with the row. So for example, if we look at P21, that's the probability that a member of the population is going to change from the jth state, which is the first state, to the second state, S1 to S2. So the rules, we now think about them as each column of the transition matrix has to add up to 1, because we're thinking probabilities, and every probability entry has to be between 0 and 1. We wouldn't have any negative probabilities, and it certainly wouldn't make sense to have a probability more than 1. That would be more than 100% chance of something happening. Here's an example. We can call this a Markov matrix, or think of it as a stochastic matrix because it's a measure of probabilities. A chemistry course is taught in 2 sections. We're going to call those sections A and section B. So every week, a quarter of the students in section A and 1/3 of the students in section B drop. So we see those numbers here in our diagram. The drop circles down here at the bottom. So here are the students leaving section A to drop and leaving section B to drop. Notice the arrows from the drops back to circles A and B are zeros because we assume once a student drops in this model, they're not re-enrolling in the class. And then 1/6 of each section transfers to the other section. So that is described by these arrows here in the diagram. So we're going to write the transition matrix. And then we're also told that at the beginning of the semester, each section has 144 students. All right, so our first entry is going to correspond with, we'll call it P11. So that's the probability a student moves from state 1, which we can think of as section A, and stays in section A. So they're not moving between section or state 1. So they start in state 1 and they end in state 1 after we've been through this process. So that's essentially the probability that the student remains in section A. So we start with 1 and we subtract out the quarter of the students who drop that week and the 1/6 of the students who transfer to section B. All right, our next entry here is P12. Those are the students coming from state 2, which is section B, into state 1. So that's the 1/6 of students right here who moved from section B to section A. Our last entry here would be P13. That would be students who go from dropping back to section A, and we see in our diagram nobody does that, so that's why this entry is a 0. Okay, row 2 corresponds with section B. So the 1/6 of students who move from section A into section B are denoted in entry 2-1. So they are going from section 1 into section 2. So we'd say that is probability 2-1, moving from section 1 into section 2, or from section A into section B. Then the next probability here is the probability the student remains in section B. That would be probability 2-2 entry. So we start with 100% or 1, and we subtract the 1/6 that moved to section A and the 1/3 who drop. And then the 0 in row 2, column 3, so position 2, 3, is because students who drop are not moving back into section B. Our last row corresponds with the drops. So 1/4 of the students from section A are going to be headed to the drop each week. 1/3 of students from section B are going to be headed to the drop each week. And then the 1 is the students that stay in the drop. So essentially what that's saying is once a student is dropped, they stay dropped. So you can see that 1 reflected here in the diagram. All right, so these values, when we simplify, we get this matrix over here, 7, 12, 1, 6, 0 in the first row, 1, 6, 1/2, 0 in the second row, and 1/4, 1/3, 1 in the third row. So the first row corresponds with matrix, section A. The second row corresponds with section B, and the third row corresponds with the drops. So together they make up this matrix. All right. We call this matrix a matrix of transition probabilities, or you can call it the Markov matrix or the stochastic matrix. And so now we're going to take matrix P and we're going to multiply it by the number of students currently in each section. So these values down here we see are the column vector 144, 144, 0, because section A has 144 students, section B has 144 students, and no students have dropped when we start the class. So let's go put our matrices over in Simpy and check out how these calculations go. So I'm going to call our transition matrix or our probability matrix, matrix P. And then I'm going to enter our values here. So those values are 7/12, 1/6, and 0 in the top row. I've got 1/6, 1/2, and 0 in the second row. And I have 1/4, 1/3, and 0 in the third row. And I can just type P to double check I've entered my matrix to match our calculation values. And then I'm going to enter the current initial enrollment, and I'm going to call that X0 or X0. So that's going to be a column matrix. So the first value is 144. The second value is 144 also, since each section starts with 144 students, and the third value is 0, since no students start off in the drop group yet. And then we type X sub 0, and it is a match for what we expect to see in the column vector. So now we're going to do P multiplied by X0. And so this tells us after 1 week how many students are in each section. So remember, the first row corresponds to section A. So section A has 108 students enrolled. The second row corresponds with section B. So section B has 96 students enrolled. And the third row corresponds with the students who've dropped. So 84 students have dropped. Not so great retention for this class. And we can see that's a match for our calculations right here. So now let's see, well, what happens after 2 weeks? Well, we can take this result. So I'm going to save this result as, I'll call it P1. You can verify, okay, P1 is the matrix we got there. And so now we can take P1 and multiply it by P again. So we can say, okay, let's do P times P1 and see what our results work out to be. Well, isn't that the same as if we had just done P times X naught? It is, because we've been through 2 weeks, we've essentially squared matrix P. The other way we can type this is P to the second power, using the double asterisk to indicate the exponent here in SimP, and then multiply that by X naught, and our result is a match that way as well. All right, and so those values, 79, 66, 143, correspond with what we have here. Oh, how come I don't have the 143? I think there's a typo over here on the sheet that I pasted in, maybe. Let's see. Oh, the 143 comes from the 84 plus 59. So we had 84 students who dropped the first week, and then we add those to the 59 students for those who dropped. All right, so that's where our 143 comes from. All right, what if we want to know how many students are enrolled in each section after 10 weeks or after 15 weeks? So this is what's known as the nth state matrix of a Markov chain. So the nth state matrix of a Markov chain, for which P is the matrix of transition probabilities and X naught is the initial state matrix, is Xn equals P to the nth power times X naught. So let's go check this out. So I'm just going to verify that my X naught is what I want it to be. I'm going to verify that my P matrix is the same matrix that I want here. It is, and so let's go ahead and see what happens after 10 weeks. So we'll have P to the 10th power times X naught. All right, this is kind of messy here, but it gives us the fraction, I believe. So we could divide to convert this to decimal. So this is our result as a fraction values inside our matrix after 10 weeks. So we want to see this as a decimal maybe to get some sense of it. So we're going to say P10 equals matrix P, the 10th power times X naught. And then you can see, okay, P10 returns the same matrix. And then we are going to do P10.eval_f with the parentheses here, and that'll convert to a decimal for us. So we see, okay, there would be about 5 students left in section A and 4 students left in section B if these rates continued for 10 weeks. Let's look to see what would happen if these continued for 15 weeks. So P15 is going to be P to the 15th power. So I do P double star 15, and we're going to multiply that by X naught. And let's check and see how P15 looks. It's a fraction mess, so we're going to say P15 dot eval function and put parentheses, and here are our values. All right, let's look what would happen after maybe like 20 weeks if this kept going. So we'll say P20 equals matrix P to the 20th power multiplied by itself 20 times to X naught, and then let's check what P20 would be, and we'll do that as a decimal. And you can see this values here are looking a little bit closer to P15. Let's go really far out. Let's go maybe P30. Times X naught, and we'll say eval_f. And then let's go to P35. So what if like 35 weeks on? I know semesters aren't long. So I hope what you see is that the values are starting to plateau or get steady. You can imagine if we kept doing this Maybe we'll go to like 99. Oh, now it's super small. And 100. So it's still super small, but it's similarly super small. So what we see here is what's known as the steady state. So we saw a little more difference than I thought we would, but we saw, okay, if we went to like 99 weeks, we get to a point where there's a little difference. So if you continue the process as we did in this example, eventually the matrix is going to reach some xn state that gets to be very steady from one state to the next. So as long as the matrix P does not change, the matrix product approaches a limit, we say, when we get to what's known as the steady state. So we will, in the next videos, explore Markov matrices some more.